one method that you can use to solve a system of equations. And then 3.8 is solving matrix equations, which can be used to solve systems of equations. So these are the two methods that really then tie into the chapter with systems of equations. In order to use Cramer's rule, though, you have to know what a determinant is and how to find it. So really today, we're just going through how do you find a determinant so that you can actually use the rule tomorrow to solve a system. So at the top it says these are only for square matrices. So every square matrix where it has the same number of rows as columns. So the two square matrices we are focusing on are 2 by 2 and then 3 by 3. Since we have solved systems of 2 equations and systems of 3 equations, so we need at least those two. But only square matrices have determinants. And the determinant, it just says of a 2 by 2 matrix is a second order determinant. So for 3 by 3 would be a third order if you see that vocabulary. But for a second order determinant, this shows you not only the notation, but then how to find it. But it is the difference of the products of the two diagonals. So a determinant, first of all, your answer is just going to be a number. So it's not like when we've been adding and subtracting and multiplying, your answer has still been a matrix. Here, a determinant is just a value for a matrix. So there's two ways to notate a determinant, and one way is to write, if you see DET in front of a matrix, so it would still have brackets, but would say DET in front, that would imply you're supposed to find the determinant. Or they look like absolute value bars, just normally we see brackets around a matrix. If you just see vertical lines, that also means find the determinant. So the determinant for a 2 by 2 is right here. This is the formula for it. And it's when the elements are in the order they're in. So you see A times D. So I call this the main diagonal when you're starting with the first element in the upper left. So it's A times D and then minus the product of the other diagonal, B times C. So just A times D minus B times C. That's the formula, and it gives an example. And there's two here. So to evaluate the determinant for a 2 by 2, again, when you see those vertical lines, correlate that with, that means the determinant. So for this one, my main diagonal, it'd be -6 times 8. And then it's always minus the product of the other diagonal, which is -7 times 10. So for A, it'd be -48. And then it'll be minus -70, which will change to plus 70. So that would be 22. So 22 is the determinant. Your answer is just a number. Okay, questions there? Okay, we just look at the second one, or you might have already kind of been looking ahead. So this one, it'd be the same thing. It'd be 7 times -4, so -28. Again, always minus. 5 times 9 is 45. And that would be -73. So a determinant, it can be positive, it can be negative, it could be 0. But that's how you find it for a 2 by 2. So then for a 3 by 3, just like we had systems of 2 equations and then systems of 3 equations was just more of a process. So a determinant for a 3 by 3 matrix is more of a process. They call it the diagonal rule, and these are the steps. So I'll kind of summarize these steps as we go through example 2. So we have a 3 by 3 matrix. We have the vertical lines. We're finding the determinant. So step 1 to use this rule is to rewrite the first 2 columns of your matrix to the right of the determinant. So when I look at this, I take my first 2 columns and I just rewrite them next to it. So it'll be like I have 5 columns instead of 3. So I just rewrite column 1. And then I rewrite column 2 next to that. And then just reading through what they have as the steps again, because I kind of combined some of these. So it's gonna be a combination of steps 2 and 3. But where you start is, again, just like up here, I called the diagonal where I started in the upper left, I called that the main diagonal. You start here as well in the upper left. But here you have 3 diagonals. So you have this main diagonal here, and then since you've rewritten the first 2 columns, you have 2 other full diagonals that are parallel to that. So I have those 3 diagonals, and what I'm going to do is in each diagonal, I multiply the 3 values, and then those 3 diagonals that I highlighted in yellow, I'm going to add them all together. So equal here. So I'd start out, I'm going to have -5 times -1 times 2. So that would be +5 times 2, so 10. And then plus the next diagonal product, so 9 times 5 is 45. And then 45 times -4 is -180. And then plus that third diagonal that I highlighted, 4 times -2 is -8, times 6 is -48. And so these 3 values are going to get added together, which I'll do in the next step. I'm just going to highlight these to show you. These are from the yellow products. And then I do the same thing with, just like up here we had kind of this diagonal product minus this one. So now it's these 3 diagonal products added together minus, if I go the other way, these 3 diagonal products. So if I start in the lower left, I have those 3 diagonals, and I would do the same thing. I would find the product of each one, and those are all going to get added together. So I'm going to start with the one that's on the left here. So -4 times -1 is 4, times 4 is 16, plus 6 times 5 is 30, times -5 is -150. Yep. And then plus 2 times -2 is -4, times 9 is -36. So those will all get added together. And then once you find these 2 sums, those overall get subtracted from one another. But make sure that you are subtracting them in that correct order. So how I have it organized, the ones I highlighted in yellow all added together minus the ones in purple all added together. So this ends up being -218 for this sum minus -170 for this sum, which I'll really then be adding 170. So -218 plus 170 means the final determinant is -48. Okay, so overall, you're multiplying, adding, subtracting, but it's knowing how to organize it. So what exactly am I adding together? What am I multiplying? What am I subtracting? All of the above. Questions on that one? Okay, there is a second example. I'm going to leave this here in case you're still writing something down or want to look at what I have. But there is a second example of that, example 3. I want you to try that one. So find that determinant. You can use that as a check that we can get through the 3 by 3 determinants correctly.
This would be 40 on the time, so this will be 40. We get combine next time. So make sure that 4 by each of these is 40. So all 3 meters are multiplied.
Okay. Final answer, double check what you're getting, should be negative 60. So 136 would be the first 3 products added together. 196 is the second 3, and then subtracting those 2, negative 60. Okay. So then again, we'll be using determinants tomorrow with Cramer's rule to solve systems. But one other thing determinants can be used for is to find the area of a triangle. So I'll go through this with you too. It says if on a coordinate plane, if you know the coordinates of the vertices of a triangle, then you can use this formula here to calculate the area of the triangle. So it shows the area of a triangle with vertices A, B, C, D, E, F is, it uses the determinant of A. So the area is 1/2 times this 3 by 3 determinant. So you can see these first 2 columns are where your coordinates go. So your first column would be all of your x coordinates. Your second column would be all of your y coordinates. The third column is always 1s. Actually, this here, I misspoke. This is not the determinant of A. It is the absolute value of A, and this is what A is. So depending on the order that you put the coordinates in, if you were to get a negative determinant, you would take the absolute value since the area should be positive. So if you got something that was negative, you're just getting the exact opposite of what you should have. So if you got 16, it really should be positive 16. So this does mean here, just because we have that same symbol, this is the absolute value of A. So if you're getting a negative, just make sure you realize it's area. It should be positive. You just take the absolute value of it, so that's positive. So if we look at example 4, a surveying crew located 3 points on a map that formed the vertices of a triangular area. A coordinate grid in which 1 unit corresponds to 10 miles is placed over the map so that the vertices are located at, it gives us the 3 vertices. Use a determinant to find the area of the triangle. So if I use this formula that's up here, I'll have my area is 1/2 times the determinant of, And so again, I just list my 3 coordinates in those first 2 columns. So I have 0, -1, -2, -6, and 3, -2. And then my third column is just ones. And from here, I'm going to find the determinant first before I multiply by the 1/2. So find the determinant first. So actually, I probably should not have written my equal sign. To find my determinant, I need to rewrite my first 2 columns. So get rid of that. Okay, and then my first 3 diagonal products. First product, because of the 0, would just be 0, plus the second product should be -3, and the third should be 4. And then my second set of 3 products, that will be, well, depending on which order you find them in, this one here will be -18 plus 0 plus +2. And then just so I'm writing this correctly, so this is giving me the determinant. I still do have the 1/2, just so I'm not forgetting about that 1/2. So I'll have 1/2 multiplied by, this product would be 1 minus this, or this sum, sorry, is 1. This sum is -16. So I'm really adding 16. So I have 1/2 of 17. So 8.5. However, that will not be my final answer for this one. Anyone know why that would not be the final answer, Braxton? Yeah, 1 unit corresponds to 10 miles. And I purposely didn't draw attention to that to begin with, because I could have done something at the beginning to take care of that. So if 1 unit is corresponding to 10 miles, what would I have to do with this value to get my area? Not multiply by 10. Logan? That would be the same as multiplying by 10. You know why I wouldn't multiply by 10. So 1 unit is 10 miles. So this 8.5, is this 8.5 just units if it's area? It'd be units squared, right? So 1 unit squared would be how many square miles? So if you think of like a coordinate plane, like 1 unit is 10, but then if you have 1 square unit, it would be 10 by 10. So 1 square unit would be 10 squared square miles, so 100 square miles. I know that's kind of written weird. So with this 8.5, just based on the way I worked through it by finding this first, to actually find the area with the units in miles squared, I'd have to multiply this by 100 instead of multiplying it by 10. So it would really be 850 square miles, or miles squared. What I could have done, and again, I purposely skipped over it when I went through it. What I could have done is if I know 1 unit corresponds to 10 miles, I could have multiplied each of my coordinates by 10 right away, and then I would have gotten the 850 right away. So a couple ways you can work through that if you are given a unit of measure like that.